Good day everyone, we are Group 8. Today I will be presenting on the bioreactor and its main components which are essential in bioprocessing for growing microorganisms or cells under controlled conditions. A bioreactor is a vessel that provides an optimized environment for biological reactions, such as fermentation or cell culture, where important parameters like temperature, pH, oxygen, and nutrients are carefully controlled. First, we have the impact control, which balances mixing, oxygen transfer, and shear conditions to create the optimal environment for biological growth and product formation. Next is the PO2 probe measures the dissolved oxygen level in the culture. Beside it, the temperature probe monitors the temperature inside the bioreactor. Next, the pH probe measures the pH level of the medium. The air house delivers sterile air, which is the oxygen supply into the bioreactor for aeration. After that, the filter sterilizes incoming air by removing microorganisms and contaminants. The air pressure scale measures and indicates the pressure of air supplied into the bioreactor to ensure proper aeration and safe operation. Next, the Enter button confirms selections or inputs in the system. The Function button selects or switches between different control functions or modes. Then, the Folder button accesses stored data, settings, or saved programs. Moving to the left side, the exhaust which releases waste gases such as carbon dioxide from the reactor. Feed pump adds nutrients or substrate into the bioreactor at a control rate. Then, the sampling bottle collects culture samples for analysis during operation. Next, the feed bottle stores sterile nutrients or media to be fed into the reactor. Lastly, the heating jacket maintains or controls the reactor temperature. The Function monitoring button displays real-time process data such as temperature. In conclusion, all these components work together to maintain suitable conditions inside the bioreactor for efficient biological growth and product formation. Step 1. Vessel removal and medium prep. First, we remove the whole vessel from the bioreactor. We open the top part of the vessel and empty it out the water inside. We weigh 15 grams of glucose, 10 grams of yeast extract, and 20 grams of peptone. And mix them together with distilled water up to 1 liter. The mixing process was done twice. Step 2. Autoclaving preparation. At the same time, the other group members prepared the vessel for autoclaving. They clamped all the tubing that dipped into the liquid except the exit gas line which remained open. The YPEG medium was then poured into the vessel. The doctor came to check if the vessel was safe for autoclaving. Lab assistant also checked the whole vessel again. It was put into a basket and made ready for autoclaving. The vessels were lifted carefully and transferred to the autoclave. Autoclaved at 121 degrees for at least 15 minutes. After autoclaving, the vessel was taken out using gloves. Step 3. Reinstallation and sensors. Then, the vessel was reinstalled onto the base unit. And reconnected to the drive system. All electrodes were connected to their respective ports, including all the sensors. The operating temperature and stirrer speed were set. Lastly, the heating jacket was reattached. Step 4. Inoculation. Then, inoculum was added in sterile condition. Before we put out the culture for analysis, we conducted the whole process with aseptic technique. Step 5. Sampling. Only then the sampling line was unclamped. The culture was drawn out by using the syringe. First, 5 mm of sample was drawn out and discarded. Then approximately 5 ml of culture is drawn out. The culture was injected into a sterile collection bottle. And ready for analysis. We collected the sample for every 24 hours. Each culture was taken in 2 hours interval.
Next, I will be explaining about the result part. This table shows the microbial growth rate measured by the optical density at 540 nanometers and biomass concentration. In group 6, the biomass increased quickly from 0.7994 mg per milliliter at 0 hour to a maximum of 1.2176 mg per milliliter at 10 hour before stabilizing. Whereas in group 8, the biomass rose more gradually, starting from 0.779 mg per milliliter and reaching 1.07 mg per milliliter at 24 hours. Next, these are the graph of optical density at 540 nanometer against time and the graph of concentration of biomass against time. This graph illustrated the change in optical density and biomass concentration over time. Group 6 showed a sharp increase during the first 10 hours, followed by stabilization, while Group 8 showed a slower and more gradual increase throughout the 24 hours. The plotted trend line confirmed that Group 6 reached its maximum growth earlier, while Group 8 continued to increase slowly until the end of the experiment. The visual comparison highlights that Group 6 achieved faster growth compared to the Group 8. Next, this graph illustrated the log phase curve of biomass concentration against time. Group 6 showed a faster increase in biomass concentration, while Group 8 increased more slowly. The plotted equations confirm that Group 6 utilized glucose more efficiently, while Group 8 shows lower growth due to the higher glucose concentration. Next, the glucose consumptions. This table shows the glucose concentration measured using the DNase assay. In Group 6, the glucose concentration decreased steadily from 1.1253 mg per milliliter at 0 hour to 0.2431 mg per milliliter at 24 hours, where in Group 8, the glucose concentration decreased from 1.104 mg per milliliter to 0.088 mg per milliliter over the same period. Next, this is the graph of optical density at 540 nanometer against time. And this is the graph of concentration of glucose against time. This graph illustrates the decline in glucose concentration over time. Both groups show the continuous decreases, but Group 6 dropped more sharply, while Group 8 decreased more gradually. The plotted regression line confirmed that glucose concentration will consume steadily in Group 6 and more slowly in Group 8. Next, the product yield. This table shows the ethanol concentration measured by GCFID analysis. For Group 6, it reached 0.1231% volume per volume at 24 hours, while for Group 8, it reached a maximum ethanol concentration of 0.207% volume per volume at 8 hours. This is the graph of peak area against ethanol concentration. And this graph illustrated the ethanol concentration against time. Group 6 showed a gradual increase, reaching its maximum at 24 hours, while Group 8 peaked earlier at 8 hours before fluctuating. The plotted regression line confirmed that Group 8 produced higher ethanol concentration, but with less stability compared to Group 6. Next, this graph shows the ethanol yield against time. The Group 6 displays a continuous increase, reaching 3.9955 by 24 hours, while Group 8 shows a lower and inconsistent yield values throughout the fermentation process. Next, I will move to the discussion part. The results demonstrate that the fermentation performance was strongly influenced by the microbial growth, glucose utilizations, ethanol production, and yield efficiency. The Group 6 showed faster microbial growth, which indicates that the microorganism entered the exponential phase earlier and adapted more effectively to the bioreactor environment. The moderate glucose concentration in Group 6 provided a favorable condition for nutrient uptake and oxygen transfer, allowing efficient metabolism. Group 8 grew more slowly despite having a higher glucose concentration. This suggests that the excess glucose caused substrate inhibitions and osmotic stress, which can interfere with the enzyme activity and reduce the metabolic efficiency. The slower growth rate in the Group 8 was consistent with its delayed glucose utilizations. Although the glucose concentration decreased continuously, the rate of consumption was lower compared to the Group 6, confirming that excess substrate reduced the efficiency. The ethanol production patterns further highlight the difference between the two groups. Group 8 produced a higher ethanol concentration at one point, but the fermentation process was unstable, with fluctuations after the peak. This instability may have been caused by ethanol inhibitions, oxygen limitation, or metabolic stress due to the excess glucose. Group 6 produced a lower ethanol concentration but maintained at a stable fermentation profile, which is more desirable for consistent bioethanol productions. The ethanol yield result emphasized efficiency. Group 6 converted glucose into ethanol more effectively, reaching a yield of 3.9955 by the end of the fermentation. Group 8 showed lower and inconsistent yield, suggesting that part of the excess glucose was divided into the alternative metabolic pathway instead of the ethanol production. This confirmed that the higher glucose concentration does not necessarily improve the fermentation performance. Instead, balanced substrate concentration is essential to support the microbial metabolism without causing inhibitory effect. In conclusion, the bioreactor fermentation was successfully carried out in both groups, confirming the microbial adaptations and ethanol production. The findings showed that the glucose concentration played a critical role in microbial growth, substrate utilizations, ethanol production, and yield efficiency. Group 6, which used 5 grams of glucose, achieved better microbial growth, higher ethanol yield, and more stable fermentation performance, while Group 8, which used 15 grams of glucose, produced a higher ethanol concentration but showed instability and reduced efficiency due to the substrate inhibitions. Therefore, the moderate glucose concentration is more suitable for achieving the efficient and stable fermentation performance in the bioreactor system. This supports the potential of bioethanol production as a sustainable alternative energy source. That's all from us. Thank you.